Welcome to Dr. Sherry's Astronomy channel. This time, the theme is, Dark Energy Spectrometer Rejects Modified Gravity Theory and Detects Signs of Temporal Variations in Dark Energy. 3 observational pieces of evidence, the Hubble-Lemaitre law, the abundance of light elements, and the cosmic microwave background radiation, suggest that the Big Bang occurred around 13.8 billion years ago. This event not only marked the beginning of space and time but also the origin of all the matter that makes up our current universe. Initially, everything was concentrated in a single point, but then it expanded at an incredible speed, forming a massive gas cloud with nearly uniform distribution of matter. As the universe continued to expand, it became emptier, leaving large holes devoid of matter, while thousands of galaxies formed clusters and cosmic structures. Looking at the nearby universe, the distribution of galaxies isn't uniform. Galaxies form clusters, and structures such as filaments, which connect galaxy clusters, form large-scale cosmic structures. Also, observations of supernovae reveal that the nearby universe is expanding at an accelerating rate. Furthermore, measurements from the cosmic microwave background radiation indicate that the composition of the early universe consisted of 68% dark energy, 27% dark matter, and 5% ordinary matter, baryons. Thus, while we have entered an era of precise cosmology, where we can measure these cosmological parameters with remarkable accuracy, the true nature of dark matter and dark energy, which together make up 95% of the universe, remains a mystery. While we still don't fully understand the nature of dark matter and dark energy, they significantly influence the expansion of the universe and the growth of large-scale structures in space. Dark energy is necessary to explain the accelerated expansion of the universe, while dark matter plays a crucial role in the growth of large-scale structures. However, dark energy, by accelerating expansion, suppresses the growth of structures. As a result, the formation of the universe's structures is determined by the balance between these two dark components. Within the framework of Big Bang cosmology, gravity, as described by general relativity, is thought to drive the growth of density fluctuations in the early universe, leading to the formation of galaxies, galaxy clusters, and large-scale structures like filaments. Moreover, the expansion and evolution of the universe are explained by general relativity, shaping the vast universe we observe today through interactions with dark energy and dark matter. In general relativity, gravity is seen as a result of the warping of spacetime in the presence of mass and energy. This is quite different from Newton's theory, where gravity is simply treated as an attraction between objects. General relativity adopts the perspective that objects move toward each other due to the warping of spacetime itself. This warping of spacetime is what we perceive as gravity. For example, the warping of spacetime around the Sun causes Earth to move along an elliptical orbit, not because Earth is pulled by the Sun, but because Earth follows the curved spacetime path. When applying gravity according to general relativity to the cosmic scale, phenomena like the formation of large-scale structures and baryon acoustic oscillations, BAO, are predicted. By observing and confirming these phenomena, we can test whether general relativity correctly explains the structure and evolution of the universe. The formation and evolution of large-scale structures in the universe are believed to have begun right after the birth of the universe. In the early universe, there were tiny density fluctuations in the distribution of matter. These fluctuations were observed as temperature variations in the cosmic microwave background radiation. These fluctuations grew over time under the influence of gravity, based on general relativity, leading to the formation of galaxies and galaxy clusters in denser regions. As a result, large-scale structures like filaments and voids emerged. By measuring the distribution and evolution of these structures with high precision and comparing them with theoretical predictions, we can verify the accuracy of the gravity theory based on general relativity. Baryon acoustic oscillations, BAO, also provide a way to test gravity theory based on general relativity. Bau represents one of the key signatures of the early universe embedded in the large-scale structure. In the early universe, photons and ordinary matter, baryons, were tightly coupled, behaving like a fluid. In this environment, density fluctuations propagated as sound waves, creating oscillations. Once the universe cooled and neutral atoms formed, these oscillations ceased, freezing the density fluctuations at that point. This process created a characteristic scale, reflected in the current spacing between galaxies. By using this standard ruler, we can measure the large-scale structure of the universe with high precision and test predictions from general relativity. On the other hand, it has been suggested that general relativity might not fully explain all cosmic observations, prompting the proposal of modified gravity theories as a potential solution. While general relativity has been highly successful, it requires the assumption of unknown components, such as dark matter and dark energy, to explain phenomena like the accelerated expansion of the universe and the growth of large-scale structures. Modified gravity theories aim to extend or refine general relativity to explain cosmic evolution and structure formation without relying on these unknown components. To test these theories and deepen our understanding of dark matter and dark energy, it's crucial to study the three-dimensional distribution of galaxies with high precision, as different gravity theories predict different patterns of galaxy distribution and evolution. To create a 3D map of galaxy distribution, it's necessary to measure the position and distance of each galaxy. While the basic observation method is simple, selecting galaxies from the vast universe and measuring their distances is an incredibly challenging project. To measure positions on the celestial sphere, images are taken. Distance measurements are made by obtaining spectra and using emission lines from elements like hydrogen, which emit specific wavelengths. However, when observing galaxies in visible light, it is difficult to acquire both images and spectra at the same time, so at least two observation devices are needed. Moreover, conventional optical spectrometers cannot obtain spectra of many celestial objects simultaneously. To address this, special observation instruments were developed. The Dark Energy Camera, DECam, was created to capture wide-field images, and this massive camera, with 570 megapixels, was mounted on the 4-meter Blanco telescope in Chile. The images obtained from this observation allow us to determine the positions of galaxies. To measure the distances of these galaxies, the Dark Energy Spectroscopic Instrument, DESI, was developed. This instrument places a total of 5,000 optical fibers at the positions of galaxies within a 3-degree field of view. The light from these objects enters the spectrometer and is recorded as spectra. Thus, this device allows the simultaneous collection of spectra from many galaxies during a single observation. The instrument was installed on the Mayall 4-meter telescope at the National Observatory on Kitt Peak in Arizona and began regular observations in May 2021. The first year of data from this survey was released in April 2024. At this time, only results related to baryon acoustic oscillations were published, but in November 2024, various cosmological analyses were reported. While the data is limited, it includes observations of 6 million galaxies that existed over the past 11 billion years. Let's now take a look at the latest results based on this data. First, let's look at the results from testing whether gravity theory might not align with general relativity. In this test, two modified gravity parameters were used. Based on the data obtained, constraints were placed on parameters showing the effects on massive particles, and the results matched the predictions of general relativity. Additionally, by combining data from the cosmic microwave background radiation and other sources, constraints were placed on another parameter describing gravity's effect on massless particles. These results also aligned with the predictions of general relativity. Thus, it has been confirmed that gravity theory based on general relativity, as proposed by Einstein, is correct. The research team is also measuring cosmological parameters based on the lambda CDM model. This model assumes that the universe is primarily composed of cold dark matter and dark energy. Cold here refers not to temperature but to particles moving at very low speeds, which are easily attracted by gravity. This property is believed to play a significant role in the formation of galaxies and galaxy clusters. Using DESI data, the material density of the universe and the amplitude of density fluctuations have been measured. The results match previous measurements. Furthermore, a new indicator related to material density and fluctuations has been derived, which has also been precisely determined. These measurements align with previous observations, such as those of the cosmic microwave background radiation, further deepening our understanding of the distribution and structure of matter in the universe. Hubble's constant has also been measured. The results agree with measurements from the cosmic microwave background radiation and the previous baryon acoustic oscillations data released in April 2024. However, they do not match the values derived from nearby universe supernovae. This discrepancy, called the Hubble tension, has become one of the biggest mysteries in current cosmology. This difference is unlikely to be due to systematic errors in measurement, as shown by Nobel laureate Dr. Adam Riess's verification using the James Webb Space Telescope, as well as measurements of supernovae affected by gravitational lensing. Thus, there may be some new physical phenomena hidden within our current cosmological models. One potential solution to the Hubble tension is the existence of time-varying dark energy. The research team is exploring cosmological models that incorporate the equation of state for time-varying dark energy. The results look like this. The values expected in the lambda CDM model are for the case where W0 is -1 and WA is 0. When examining the measured results, there are slight differences depending on the data used, but they tend to deviate from the lambda CDM model. This suggests that models assuming time-varying dark energy provide a better fit to the observations than the lambda CDM model. However, the confidence level is around 2.5, 3.4, and 3.8 sigma, meaning that it is not yet high enough for a definitive conclusion. A 3 sigma confidence level corresponds to 99.7%, but in many experiments in physics, a confidence level above 5 sigma is required, so further verification is needed. DESI is now in its fourth year of a 5-year observational plan and aims to observe 40 million galaxies by the end of the project. The current results are based on the first year of data collected by DESI, but data from the first 3 years are still being analyzed. Next year, the latest measurements on dark energy and the history of cosmic expansion are expected to be released. We are looking forward to further progress. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.